All right. Thank you, everyone, for joining this meetup paper. And this is, I think, the second session or second meetup for this paper. In the first one happened about a couple of weeks back. People who are not, joined that, please feel free to join the recording. I mean, see the recording in the Support Vectors YouTube. All right. So what we do today, we'll continue that sort of the paper reading, and then some of you who are joining, I will have a quick intro. But also today is more of continuation of from the previous session on this meetup. So this paper is called Agent Lightning, and then this is to train any agents, AI agents, right, using the reinforcement learning. And a lot in the meeting, last meeting, I do remember a lot of questions came about why do we need to have a training the LLM for the agents? Why not fine tuning versus the regular prompt? So there are many questions. I think some of the meetups attendees were asking. So I asked them to refer to what we call layered approach, right? I mean, you whenever you want to think about fine tuning, first make sure that you go through the approach of whether prompting in context learning and prompting changes, and then you come to the fine tuning, right? That's how the layered approach of deciding that fine tuning is a process by itself. So in this meetup, it starts with the idea you already decided to fine tune for some reason, and then the reinforcement is the preferred methodology for fine tuning, and can be used by the agents. So that's a starting point for this paper. Now let's just to rewind or refresh what we did last time. We looked at an example because having an example always makes sense. We looked at one of the flight booking example, and then ask the problem of how this fine tuning using the oral will help, right? That's a starting point for today's meetup as well. So just to next 5 minutes is about a little bit refreshing, and then we'll go into the focus of today's meeting is about why we need to be training what we call multiple training set, right? And then what is the reward model? And then what is GRPO kind of a reward is beneficial in this oral training. And then finally, we tie that with the agent lightning framework, right? So that's my goal here. So, I mean, the framework itself, from if you think from black box approach, is pretty simple, but a lot of foundational aspect of inside that it's better for us to know so that we understand the framework, what it is doing inside. Okay, so now what we do, we post the problem example, right? Just for a few minutes. And what's the problem we are trying to go into the details in today as well. Is an example of one user query. Let's say you build a chatbot, air ticket booking chatbot, right? And then you're asking this something like book me a flight from New York to Paris for under $800. This seems like a simple query, right? And then but it has a lot of things behind that. One part is, of course, our AI copilot chatbot need to understand the language part of the sentence, and then it needs to reason, and reasoning also includes the steps, planning the steps and execute the steps. As part of that, it needs to be knowing what tools to be using, and then without too much of input from user, it should able to continue and finish the task. So this is not a simple QA task. The agent must handle multi-step workflow, and make a real world API calls and respect multiple constraints. Constraints could be, for example, under $800 is a constraint, and then next weekend is a constraint, and then recover from edge cases and errors, and then when to ask the human for help. All the things that this agent needs to be keeping in mind. So this is not a simple QA. So now, um, in this context, why do we need LLM or fine tuning the LLM? So that's the biggest question, right? So for that, why don't we go through some, and just to refresh your mind, Think about this and then try to answer a few of these questions if you could. If you have read the paper and then paper has a lot of references, this might be very easy for you to answer. Let's go this way, just a couple of questions. Let me just show you once again. I'll take you to the question and then try to see whether you remember last week, sort of the refresh. Okay. All right. Let's talk about this first one. What's the main limitation of current oral methods for LLMs, like those used in DeepSeek RM, right? What does it mean? What is the limitation of current methods used in oral? So oral is a reinforcement learning, right? So what the question asks, if you can answer by thinking that this paper is agent lightning, is if you have read the paper, it is proposing that multi-turn task is harder to train, and it needs techniques, some of the techniques outlined in the paper, such as, right, what we call credit assignment, equal credit assignment. Last week, in the first session, we touched upon that. So there has to be a technique called equal credit assignment. Things like that need to be considered, for proper training using the oral method. So the traditional methods don't have that. The traditional oral methods, I mean, when you say traditional, the one that is sort of being basic oral methods, don't consider, the multitask turns, which is very needed for the agents. The AI agents take multiple turns, multiple tasks, and then, but the traditional oral consider only a simple task or single turn task. Okay, what's the answer? I think the answer is B, right? They are designed for a single turn task. The current oral methods are designed for single turn task. Why is that? Yeah, starting point for our discussion. So AI agents need a multi-turn task. So what is multi-turn task? Multi-turn task are exactly, this is called multi-turn task. Okay. So the AI agents, which is are doing complex solving problem, goes through the multiple task, multi-turn task, and then multi-turn task, training oral on the multi-turn task is definitely approach that agent lightning make it easy. So that's a context of the whole paper. Now rest are details. Okay, how it's going to do, right? Let's talk about that. How it's going to do the agent lightning architecture. So there are two parts. How the agent lightning architecture is going to do. What are the concepts behind the oral for the multi-turn task, right? And these are two aspects. One is theoretical foundation. Other one is the practical tools, which is agent lightning, making it easy to do that. So we are going to go first a theoretical foundation, and then in the architecture of agent lightning, you can easily figure out once you understand the theoretical foundation. All right. So, but the architecture of agent lightning, just to set a little bit, is going to be like this, and then we'll have a pause, and then we'll and then ask for any clarification, and then we are going into the paper's theoretical foundations. But right now, since I said there are two aspects, one is the sort of the tools aspect. This is a tools aspect of the lightning server. So again, we covered this last time. So the idea for the last time is to cover this tools aspect, and then this meeting is we are going into the theoretical foundational aspect. So what is it from the tools aspect? What we are saying is, there are you write your agent using the Lightning client. Let's say you develop an agent, right? Using a LangGraph or Crew AI, and then what you're going to do, you're going to wrap it around. How do they wrap it around? It's a very simple, programming calls, but you wrap your agent using the Lightning client. Okay, that's number one. That is this side, right hand side. And then, for example, your agent is called RAG agent. Let's imagine you developed a RAG agent, and then you initiate or run the RAG agent using the Lightning client. So that's the idea. And then in the left hand side, you have something called the Llama as a reasoning engine. So again, here also you wrap the Llama, you start the Llama server or any of your LLM server, which is your open source LLM server. By the way, when we talk about training or fine tuning, we are talking about the open source LLMs, right? I mean, we are not talking about OpenAI or Gemini. It's about all the LLMs which you can download and then you can fine tune that. So we are talking about that LLMs here. So you wrap it around this Lightning server. The Lightning server has a lot of these algorithms inbuilt, Lightning RL, some of the trainer, things like that. It's all credit assignment. So these are all the theoretical foundation we are going to learn. But the important thing is the Lightning server by the Microsoft will take care of many of those, heavy tasks and then help you to fine tune. So these two are going to work together, and then as part of your training process, they are going to train their LLM. So that's a tools point of view, right? So and before I go to the theoretical foundation, let me pause here and ask you guys any questions on this so far. Because if some of you joined only today, it may be a lot of information, but again, this is a second session on this topic. Okay.
I have a question. Excuse me. I have a question. I'm curious about the RAG agent. Like, what context would it be storing?
I mean, context, you develop your own. If you take an example of flight booking, so imagine the flight booking example I'm telling is a RAG agent. So you can imagine that. What context it's storing, whatever the context behind the user, right? It may not be okay. In this example, it doesn't fit the RAG agent. RAG agent usually we mean is you have local vector database, right? Semantic search. That's what we mean. So the light this you can say in this case the user's profile maybe in the RAG, right? Some of the users interest and then things like that. You can imagine it could be part of the RAG, but yeah, the example doesn't fit in really, but yeah, for this example doesn't fit in, but you can imagine your own RAG project, right? In your RAG project your semantic search is happening, and then also that RAG project needs the tools to go to SQL. There are many things you can imagine, um, but yeah, that's behind the RAG agent.
Yeah, that's why I was a
Uh,
little confused because, like you said, vector databases. So I wasn't sure, but
Yeah,
uh,
see. mm,
yeah.
RAG means what? Retrieval augmented generation, correct? Whenever we say RAG, it's always mostly about, for the user, when you ask a question, go to the internal sources of the documents, right? And then get the context. The context could be about the user, right? Context it could be about the question that we need to answer. So that is called RAG. Okay, and then you're going to call LLM to answer that question, right? That's right. Um, so yeah, I mean, I think we are talking a lot of foundation before we come to this stage, right? At this stage of agent lightning, and I am expecting all of us to understand a simple RAG, advanced RAG, and what agents. There is a lot of overlap, but also conceptually these are all different. Now, RAG is you cannot call RAG as a agent. RAG by itself can support a chatbot or a copilot, but the advanced version of that is called agent. The agents now can reason through and do in a loop, react loop, and until it solves a problem, it can make multiple steps. So that is the coming towards the agents. So there is a spectrum, what they call, agents of L0 to L5. You can say that layer 0 agent and then going in the complexity towards layer 5. These are terminology used in the industry, is a high level of autonomous sophistication. So yeah, I mean, yes, these are all the foundation before we need to be clear before we coming to that at this point, right? We are now fine tuning. I hope I answered you, but it's a very deep question, right? I
I
mean,
didn't realize it wasn't that innocent. I thought it was but yeah, I mean, I you could probably do without a RAG agent too. I don't think it would hurt you too much here, but yeah, that answers it. Thank you.
Yeah, yeah, exactly. So this is just an example, right? It is some, yeah, correct. And then the flight booking example, let's call AI agent for flight booking, right? Doesn't need to be a RAG agent. Okay, so with that, let's see,
I have a
yeah, hello, yeah,
have a quick question. Can you please define what you mean by fine-tuning? Is it retraining the large language the
yeah.
LLM in post-training to modify its weight according to new information, or is it uh, more like instruct the LLM by increasing the context? I just want to understand what level of fine-tuning what you mean by fine-tuning, basically.
Correct. Yeah, that's a great question. It goes to the foundation, right? Foundation aspect, even before, this paper starts that. Yeah, fine-tuning here means in this context, the idea is we are talking agents. Agents need to have some amount of intelligence, right? I mean, that's the idea. Agents need to have a reason through. It may use a bigger LLM like OpenAI, but the idea is, idea behind AI agents. AI agents are all, AI agents, domain specific or use case specific, would be better served by the local LLM, which provides a reasoning that's specific to the domain. If you're insurance domain, and then suppose the agents need to make some reasonable intelligence for some action, instead of contacting the big LLM, it benefits from your specific use case. That use case reasoning, the idea is we can use a local LLM. I use the word local LLM. And then you somehow incorporate that reasoning that is not available in the bigger LLM into the smaller LLM or local LLM, and then use that for your AI agents. So that's a starting point of why we need fine tuning. Or you can say why we need a local LLM for reasoning. So instead of saying fine tuning, ask. I think another way to put is, for my AI agents, better to have a local LLM which provides more great reasoning, crisp reasoning, the way I want rather than the bigger LLM. So if you are convinced about that statement, then now you are in the process of training that local LLM. Now, what does it mean training? Training means uh, obviously you have some data set, right, that provides that reasoning which is not available to the bigger LLM. It could be your own thinking process, your what they call agent skills, right? I mean, nowadays the agent skills are becoming a popular term. So somehow you have those process and skills, and then acronyms, and then knowledge sources, which is way different from the open LLM, has that. So when you're convinced, when there is a proof of that happens, now you're fine tuning the local LLM. Now, why that benefits you? Because it will make your AI agent simple, right? AI agents now just deal with the local LLM and get the clear reasoning power. Instead, it may struggle to do the same thing with bigger LLM. So I want to pause here. Again, these questions comes to keep on coming, right? Why do we need fine tuning? Again, as I was saying, there are many reasons, and one of the reasons is you want to give a very clear. You want to have a very clear reasoning. When I say reasoning, the steps to take, and then planning steps and the reasoning steps that you can somehow make the local LLM work for you. So that's the context. Internally, it is using LoRa adapter concept. Those are all techniques. That means the neural network in the LLM, Llama LLM, will be changed using the LoRa technique. LoRa is an adapter. That means it adds some more neurons to the Llama. It doesn't change the basic characteristics of the llama, in this case llama here, but it adds more neurons and make this behavior different for you. So that's the idea behind this.
Okay, thank you.
Yeah,
Very clear. Thank you.
correct. Can I'm going to pause because my dog is barking. I'll be back once again. Okay, so I'm back. So let's go into detail now.
I
So
also
now,
had one
Krishnan, I
question
think
as well.
Stephen has a question.
okay. Hi, Stephen.
So this is my first meeting that I've gone to for this. So forgive me if I don't have enough context. But I know with reinforcement learning there is like penalties that are applied to the actions that like an agent would do if it does something wrong. But outside of that, is there any other mechanism in your system that prevents or reduces hallucinations among agents?
Yeah. So oral is one of the definitely the technique to reduce the hallucination, right?
Hmm.
And I mean, people are trying with prompting, with so many constraints, they put constraints in the prompting. So that is exactly when you start putting a lot of constraints in the prompting to reduce the hallucination, the prompts will become 2, 3 pages now. You can,
Yeah.
right? And then at that point, somewhere you need to decide, this is becoming too complex because you are trying to force the behavior. What happens when you put a lot of prompts? Then, the intelligence slowly going away. Then it become monotonous. Then your chatbot always answers the same way.
Hmm.
There's no variation or variety. There is no humanness in that. So people start putting those prompts, constraints, then it becomes monotonous. It doesn't become like a human or human type agents anymore. So that then at that point you need to decide. Okay, so looking maybe is it fine tuning will solve the problem, right? Instead of forcing the LLM to behave the way I want. I mean, before fine tuning, can I somehow make it a better LLM where I don't need to put so much prompts? The LLM is now smart enough to already the constraints are built in. So that's another way to think. I'm ready for the fine tuning. All right. Okay. That's
Okay.
okay.
Thank you. Thank you. I guess so. What you're saying is it's sort of up to whoever's inputting that prompt to reduce those hallucinations, given like a trade-off that this person would have to use as to whether or not they want like a too specific prompt or give the agent more freedom and run the risk of a potential hallucination.
Yeah, yeah. So that's true. I mean, yeah, I mean, exactly. So the hallucination may appear because of many reasons. So one of the reason I told is that is your LLM is not working out the reasoning capability, right? Is not fine-tuned or does not work for your planning and steps. And then hence the and also the world knowledge that LLM has may be different. But the hallucination has a lot more things. It is due to the way the probability distribution of your data in the LLM is trained. So and the nature now, the idea is LLMs are always stochastic in nature, right? What is stochastic in nature? If you ask the same question to the LLM 100 times, uh, I mean, without any constraints, right? You just have a simple prompt, you ask the LLM, and then you would see different answers most of the time. So that tells you the LLM, right, in which you're dealing is a stochastic in nature. Um, and then you put prompts and constraints in the prompt to make it a little bit workable for you. But still, it is stochastic. That's the nature of it. So yeah, that's one way to see you arrive in a decision that, yeah, can I fine tune so that I don't have the hallucination? That's one way to think about deriving to the point of fine tuning.
I see. Okay. Thank you.
So now, yeah, thanks for the questions. Let's go to um, the key problem, because if I start repeating, then I'll be repeating the same thing as I did in the last time. So, but I'm going to go to the credit assignment problem. Okay, here because a little bit advanced concept, but I hope the people who are joining first now will go back to the previous recording and then continue from there. So this is one of the important thing. All right. I mean, this is something for new people. It is you need to catch up, but I hope I will provide you enough information for you to go back. So the learning, what we say that is oral does not reinforcement learning does not just need a good examples. It needs both good and bad. Okay. So the concept here is now we are going to talk about oral reinforcement learning. how the reinforcement learning is, what are the components of reinforcement learning, and then the key thing we are going to say here, right? What we call credit assignment. Again, in the core of the problem, you need to remember multi-turn task is hard to. There are many. It is somewhat different to train oral instead of the single turn task that many of the people are already doing it. I'm just bringing in the root of the problem. So in the case of multi-turn task, it's very difficult to think about how to reward. That is important starting point. For example, let me see. I'll show an example and then we'll go here. One second. What is a single turn and multi-turn? So, for example, when you ask the LLM, something like simple question, what's the 15% of AT? This is a single turn task, right? Well, there are many ways to give some training in a SFT technique, even oral techniques are there. And now the focus is not this. In the multi-turn, okay, multi-turn, let's say that the example we took. In this example, the user is asking, book me a flight from New York to Paris, right? There are steps. Step one. Step one is going to ask the LLM, right, about give me the best search to satisfy this problem. And then imagine there is a step two, and then it basically using the MCP tools to get that. There are step three. Then the chatbot then tells the LLM, there are 15 flights I find. What's the best under things like that going. So these are all multi-step, multi-turn tasks. So now the question here is, you just imagine there are multiple tasks AI agent is doing, 5-6 steps. In the 5-6 steps, right? If it finally settle down, let's say that there are many possibilities. One, the chatbot will fail to may succeed in booking you a great flight, right? Or it might fail in getting you a great good flight, satisfying consider your constraints. Or it could get stuck somewhere in the middle and then ask more questions for clarification. So there are 3 or 4 possibilities, right, for your AI agents to behave. Now, if here is the core of the problem. So when you are developing such agent, and when you are dealing with the OpenAI LLM or not fine-tuned LLM, then what happens is you would see a lot more failures. AI agents, will fail to make a good flight recommendation, and then it will try hard. It may go in a loop again, and then again it might fail. So the AI agents are going to struggle now when you have the multi-turn task, and then you are going to use the normal LLM or open LLM. Then if you are into the AI agents building for such complex AI agents, you will see that people are figuring out AI agents for complex multi-turn, multi-step. He's only 10 to 15% success. Not much. AI agents are very successful, very success rate, and I mean, people are happy, users are happy. It's trying to replicate or some real human persona to become an AI agent. It is still a hard problem to solve. There are only it is as per the report, only 20% of the time it works. So why is that? The reason is that is in the multi-turn task or complex workflow task, we don't know how to train the LLM. So why it is hard to train the LLM? So the question that is coming to all of us is, when you have so many tasks, which if one of the tasks is failed, that means what? If one of the tasks is not behaving correctly, imagine there are 5 tasks. Imagine that, let's say that you somehow got a good book, in this case ticket booked, right, under $18. Doesn't mean what? Doesn't mean the steps in between all of them are great, is a question. In the same way, if one in the failure scenario, you fail to get a good ticket, but what does it mean? Some of the steps in between, is it bad? So now is the thinking come, right? So how do we now reward each individual steps in a multi-step, right? So that LLM starts learning. In this case, LLM means, of course, the Llama or local LLM. Now, in order for LLM to start learning, which steps are good, which steps are bad, which combination steps are good, right? Which combination of steps are bad. How we need to start giving some training data to LLM. But if you happen to give some training data to LLM, saying that in this workflow, right, this kind of workflow makes sense, for the problem you have, then over the time inside the LLM brain, neurons will get wired appropriately. And then next time when you pose a question, it's going to get you the right workflow, right task in the steps. So that's a problem we are trying to solve, right? How do we tell the LLM these are the steps which will take you to the good answer. These are the steps which might not take you to the good answer, maybe fail, bad answer. So that is the core of the oral training in the multi-step in a step process. Okay. So how is other problem? I mean, I want to pause here. There is an example they say that if you take let me see whether I have an example, right? Uh, Instead of booking, there is another one. There is an example which might resonate with you. One second. Okay. All right. So let's look at this basketball game, right? I mean, it's just if you're not getting that flight steps, right? It's like if you're in sports, you will understand, right? In the sports, finally you reach the goal, either a shot or some, you get a good hit. But in the case of basketball, many players are working, collaborating together, right? And then finally you get to shoot, right? I mean, in the basket, in the ball in the basket. So now a lot of things can happen, right? Who gets the credit? There are 3 or 4 players working together, playing together, and then making this, right? I mean, if a final guy able to put it, does it mean reward goes to only that person? What about the person who passed the ball in the beginning? Right, that's a question, right? Who should be in this case rewarded, more than rewarded, as a team, how they learn together, right? In the case of failure, same way, if the last person failed to shoot the ball, what does it mean to the team? So that's a good analogy, right? In other words, there are many possibilities, variabilities are there, and then how do we reward in this case, players, who are shooting the ball properly? I mean, able to do it, versus it is not. So this is just an analogy to give you. Start thinking about how to give reward, right? You can take it to your enterprise workflow and then think about how to reward the LLM for the actions or steps it's going to take. So we'll go through this one more time when this steps come through in my sequence. But let's go to the credit assignment problem, right? Okay, now I want to connect the dots here, right? All these things, credit assignment, what's going on inside the multi-steps. Why are we talking about, right? Now, initially, we are talking about agent lightning framework, and then I switched to this theoretical foundation. What's a connection? So the agent lightning framework inside, it's all doing these kind of things. How it's doing, I need to connect you again at the end. First time I explained the agent lightning is a framework available to train the RL, I mean, to train the AI agents LLM, and there are many blocks in that you need to understand. And then second, I'm explaining, there is a multi-step in the case of AI agents. There is a multi-turn task, and then training the multi-turn task using the RL. You need to have theoretical foundation. And then third, which is more of a techniques, is about how we enable the agent lightning to trace the steps automatically without coding. And now you just start in a chat bot, and then you start talking to the AI agent. Agent lightning will figure out, as you're talking, it figure out whether you are successful or not in that conversation. At the end, it's becoming a happy conversation, or is it becoming a bad conversation? The agent lightning framework is able to figure that out. It has a traces of that. So then using those traces, it trains the LLM automatically. So that's the power of the framework. So first is the block. So, now we are talking a little bit of theoretical foundation. Third one is a technique in the agent lightning, which actually does that. So now we are still in the theoretical foundation now, right? So, okay. All right. So travel agent example, right? I mean, let me pause here. Are you guys with me now? I mean, there are many parts to this puzzle. Right now, I'm trying to give an idea how to reward the steps. That's where we are right now. Any questions?
Christian,
Yeah.
so you're rewarding and updating the weights the same time you're talking to an agent?
Exactly. That is yeah. The agent lightning is going to take care. Yeah. So that is the another. I need to connect the dots.
Mhm.
Agent lightning framework. First, we'll wait for you to say, let's call it as a testing phase, if you want to call it as, right. You developed an agent, a agent without any training, right? You developed an AI agent without using the llama as it is, right? When you go back to the llama here, let's go
Mhm.
back to the diagram here. So in the step one, what you're doing is, um, basically, let's start with you develop the agent, you programmed the agent, here it's called RAG agent, right? Let's call
Just a basic agent. Okay.
yeah, let's call you develop the RAG agent, right?
Okay, I think I got the reason why you prefer the RAG isn't here. You just, I see here, we just take the basic model, Llama model, right? And as we uh, talk to the agent,
Yeah,
I think we get a contextual data and then passing it to the
yeah,
Lightning server.
yeah. Exactly. So that's the automation they had done. So without this automation, I mean, these are all the good questions, right? People who are done, let's say the training on a Llama or local LLM, they might have done differently. In other words, they come up with the training data, right? They have a training pipeline, and then they start the training pipeline, right? And then it will update the Llama. So that's one way to do that. So here they kind of integrated that to make it easy. What they are saying is, you develop your agent, travel agent, and then you run it under the lightning client, right? And then they wrap your LLM through the server. Now we'll take care of that magic, right? I mean, there are some what we call entry and exit points. And there are some instruction you need to tell, saying that start training, and then it will basically, I'm going into more details that might confuse people here, but I'm going to pause here. But there are ways in which you tell the lightning server, hey, try this task, and then it goes and automatically try the task many times, what they call rollout, and then finally train the LLM. So I mean, those are all techniques in my opinion, right? Not to be bothered right now. So right now the foundation is how the training happens, right? In a multi-step, multi-turn task. What is that reward going into that model? I mean, that's a foundational aspect. But if you are coming from, I don't care about those things. I just want to have a practical experience, right? Then you can set it up in 10 minutes or, half a
Yeah.
day. So,
But when do you know that it's finally ready?
what is it?
When do we know that it's finally qualifies for the
Oh
final?
yeah, that's true. That is basically a good question. Um, so the way it is currently, I made it in my test program is to tell that, saying that run 100 experiments. Okay, I just manually say that for this task. For example, the book the flight task, right? I tell, use this flight a book task, call, try it for 100 times and then train it. So I just, the 100 times or 1,000 times, that you need to have a separate evaluation framework to do that. Okay, but the Lightning client and the server allows you to say, try this task for n number of times, and then fine tune. That's a
You mean
configuration.
times in the sense you're saying the actual trajectories?
Exactly. So when you say 100, that means it generates 100 trajectories.
Okay. Yeah.
So how much is enough? I don't have the answer, right? It depends upon each use cases.
Go back to the other tab that you were on with
Which one? The flight booking or
it was the let me just look here. The
this?
credit assignment problem.
Yeah. So that is what I want to go deeper today, right? I mean, that's a goal of today is to go into the assignment. Let's go into that. That's a goal today. Yeah, here, I have failure cases and successful case. But here, what we are saying is this final reward is one. Okay. But I'm asking you to think, there are three reward system that generally talked about. One, are you able to say, right? All of them are equal reward should we give? So that's a question I'm posing to you. Or should we give a different reward for each step, right? Or should we give more reward to the first step and then as less as we go? Or the other way, should we give the reward of step 5 lot more weightage than the first step? So there are many concepts here, right? Which step is better, or which step is crucial and which step is not that crucial. How do we decide, right? I mean, it's very involved theoretical, research context, I guess. Research concepts are there, but this paper proposes, not me, this paper, Microsoft, saying that let's give equal credit. So if the final answer outcome is favorable, in this case it booked the ticket under $800 correctly, then give the reward equally to all the steps. Okay,
Each
that's
for each step. Yeah, I remember that was a very
yeah,
interesting claim of the paper. So
yeah,
for each step, I just want to clarify, each step is one single agent, and we would assign a good or bad either 1 or 0 for the weight.
yeah.
And then would we use LLM as a judge per each step
Yeah.
to see if it's passing or failing?
Correct, exactly. Okay, I mean that's what I wanted you guys. This one particular document is the most important. Let's go through that whether we get it right. Once we get it, then everything is small details. Okay, the key insight is learning requires comparison. Oral does not just need to see good examples. Oral means reinforcement learning. It needs to see both good and bad attempts to learn what it works. What that means, we have a task called book a flight from New York to Paris, right? Now the agent is going to try 4 times, 4 rollouts. But I can tell agent light, hey, can you try this for 100 times, right? That's just a configuration. And then in this example, we are somehow making the agent lightning, framework. Hey, for this task, try this task 4 times, right? And then learn from that. Imagine you say to this agent lightning, hey, this task, try it for 4 times. And then every time, I mean, the first question you need to understand is, why do I need to train 4 times? Why do I need to say the same thing 4 times, right? That's the first intuition you need to have. Why? The background or the basic idea is LLMs are stochastic in nature, right? You tie that concept in your mind. When I ask the same task many times, LLM is going to make different decisions every time. Okay, I mean you have to believe that, you have to see that LLM doesn't give you the same answer for your one question. But if you imagine you have 5 questions, in every time in the 5 steps, if it makes a different decision, the combination is so huge, right? I don't know the mathematically 5 power something. So as the number of steps are high, more, and then if each steps has a stochastic process in nature, then overall LLM is going in the whole task, which is AI agents, right, is going to have a many failure scenarios possibly. Instead of saying failure scenarios, you can say there are many stochastic combinations will come. Okay, that's the foundation of this paper, right? LLMs are inherently stochastic. even for single call. But in a multiple call, it will even screw up. So when that happens, your answer is unpredictable. In such situations, why not we consider oral as a technique for multi-step process, multi-step, multi-turn task, and then somehow tell the LLM, learn this as a whole task, not as a single task, right? That's the essence of this reinforcement training for a multitask, multi-turn task. Okay, so now the trajectory, some of you want to still thinking that I still don't get this trajectory. When you call the first time, the trajectory you just need to assume, right? Trajectory is that you are asking LLM, give me the good search, right? That's the first call. The first time in this trajectory one, the LLM gives you New York to Paris flights March 15 to, it says, it returns this query. Basically, we are asking LLM, hey, I need to book a flight to something, but give me a best search query. LLM gives this search query, right? I mean, this is a comment from us, but LLM gives this. But in the same trajectory too, LLM is not giving that. LLM is stupid now. LLM is giving flights to Paris. The answer is flight to Paris, right? And then another trajectory, that means another sort of another try. LLM gives something else. JFK to CDG March 19 is round trip under 800, right? Good. This is irrelevant. It gives some other output, right? In another trajectory, it somehow it became hallucinated. Instead of giving you a good response, it says, I will book the Delta flight. I mean, I didn't ask the LLM to book it, but it's giving different answer. So how many of you believe that LLMs are stochastic, right? Every time for the same question, it gives a different answer. It's not completely different answer. It is somewhat related, but it is still different. Do you guys agree?
Agree.
Yeah, why? You can imagine, another way. Imagine that there is a probability distribution, right? I mean, I will show you another diagram. I hope I have that. I want to show the probability distribution. One second. Then I'll tie the story. Okay, maybe this one. No, one second.
It looks good.
You're good?
Yeah.
All right, so but I wanted to show one second. I think if I not, it is going to come when I go through that. Let me show it. I have a slide which shows the probability distribution, right? That's what I wanted to show. But that will be a good way visually to visualize. But I'll wait for that to come automatically. So now that we all believe that, what's next? This is good, but what's the use of this information right now? So right now, what we are attempting to do, okay, by having all this trajectory, let's say you take 100 such trajectory, and then give it to LLM, give a proper reward to the successful one, so that after the training, you will never get to this trajectory too. That means after the training LLM with our own reward model, you would not see the trajectory too. Or you may see it in low probability. You will see more successful trajectories. Let me put it that way. Without training, these 100 trajectories will come and go at any order because of the stochastic in nature. But after you train it, you tend to see all successful trajectories many times, when you run it. So that is a key
So
learning.
yeah.
Yeah.
So you're saying that it'll converge?
Yeah, exactly.
Yeah. Okay. I have a couple questions. So we have the LLM call 1, LLM call 2, and we talked about how each of those is a step in the each one of those is a step that is then assigned a reward. And so my first question is, are we having like a parent LLM that's using the LLM as a judge, looking at all of the full steps, to then understand if it's passing or failing? And then for each step that's an agent, right? And we're also fine tuning at the LLM level of that agent as well, like in those weights as well. Is that correct? My understanding.
Exactly. Yeah, that is true. But this is what I wanted to show, right? I mean, for example, if you go to LLM, if you can able to generate this, I don't, this may be a little bit fictitious one, but let's say if you're able to somehow figure that out from LLM, when you ask this query, generate search for any, okay, somehow the LLMs are trained from the old data. So 35% of the time it's going to give the New York to Paris flights, right? And then 50% of the 12% of the time something it will say. So essentially we are trying to rewire this probability distribution. Okay, that's all. And that is what we are trying to do by training. So the way I am imagining, like this, for every query we make LLM, this kind of probability distribution comes in mind. And then when you ask a question, it's a stochastic in nature. It can pick up the answer. It can pick up this answer. It's going to pick up 22% of the time. It can pick up this one. It's 12% of the time. But how do I change the distribution? To make the bad ones come in the bottom, good ones come in the top. So that's all we are trying to do in the reinforcement learning training. That's a bottom line. All right. So back to this. Now that I tie that story, that's all about the reinforcement, right? I mean that's a key concept. Now what is it? Now let's give a trajectory reward. So what we are saying is in the failure case, we want to give. We haven't given the reward to each step yet, but I'm just saying in this case reward is 0. And then third one is a successful trajectory. Though some of the output from LLMs are a little bit different, but still it's successful. And as far as somehow it is successful, then we are doing that. So these are all the different trajectories. Now what do you do? This might be happening within the agent lightning framework. It collects all these trajectories, and then now it started giving the assignment. Okay, because we believe in this paper believes if it is a successful trajectory, I'm going to give 1 to all the steps. Okay, that's the idea behind the paper. But we don't, there are many other special use cases where this may not work. But I mean, that's advanced topic. But for now, let's imagine we are going to give same credit to all the steps if it's successful. Okay, so now a little bit advanced called GRPO comes into picture. I'm going to come to this later a little bit. Okay, so I'm going to cover it, but imagine there is first is the giving the credit assignment, then what happens in LLM, right? I mean, now if you're taking the ML course, you know that the gradient loss needs to be calculated, the ML weights need to be updated. I don't want to go into that because you really need to have some foundation for the gradient loss and stuff like that. But this leads to finally the loss calculation. What is happening now is I give each steps a reward, then I do what we call GRPO, group relative policy optimization. I'm going to talk about that. And then finally, we apply that to the gradient loss. So I think that story I need to tie it. But let's go back to here. One more second. We will cover. Yeah, this is what we covered. Okay, we have covered this right now, and then go to the next one. I mean, it may be a repeat here, but let me see whether it's a repeat or not. Okay, this is a repeat. We covered this concept. Okay. All right. This maybe it's a question to ask, right? So we propose that reward all the steps. That's what we proposing. The paper is proposing. We also agree. In the final reward is a team outcome, right? Every step on the team should share the same reward. I mean, this is a basketball analogy, but every step in the whole step needs to have the same reward. Okay, we kind of know that, so we can skip that.
Krishnan, I think there's a
Yeah.
question. Someone has Piyush has his hand raised.
Can I ask a question?
Sure. Let me
Uh,
yeah.
So, like, is there a chance that it will lead to overfitting? Because looks like we are training the model with very specific example, Paris to here and all of this. Do you think in this case it will be able to, let's say, figure out some totally new destination or some totally new origin, or would it lead to overfitting in the model and then it will become very good for the trained example, but will have no clue how to handle the more general cases.
Well, yeah, I mean that's a good question, interesting question. So, see, I think you may be coming from traditional ML model, right? Where overfitting
Mm-hmm.
happens all the time. But in the transformer architecture, because it's a generative in nature, right? I mean, because of the temperature and generative in nature, that overfit is a problem. But because inherently it has a generative capability, the stochastic in nature, that is less of a problem. So just because here I'm training the New York and then say other doesn't mean that it does not going to work, because LLMs have, you can imagine two different things. One is a knowledge, world knowledge. Other one is a reasoning power, right? How the LLM has a reasoning power. Reasoning means what? If you give an example, I can, that example has a good steps, right? One, two, three. But if for another example, completely irrelevant, we still those steps apply. LLMs are now able to do that, right? You're seeing that. That's why the generative nature is helping. So your question, most is applicable to the traditional ML model, not the generative model. Here, is it making sense? Let me pause there.
Yeah,
You,
no, it does. It does. But in this case, let's say if I'm actually developing this application, so does that mean I have to generate a exhaustive
no, no, no. You have to
list
generate.
of tests?
Yeah, no. You have to generate both positive and failure scenarios. You don't need to generate, let's say Bay Area to LA, right? You don't need to do that, but it needs to have a good amount of failure and positive scenarios.
Right. But does it have to be for like the exhaustive set of cases? For example, from every destination, from every origin to every
I'm saying
destination with
no, no,
every
no.
possible constraint.
I mean, well, then there are you have to go deeper to the question, right? I mean, let's say in the case of flight booking example, uh, right? I mean, you trained for this, our example, right? Our example says that book a ticket from A to B with the constraint called less than 800, right? And then we can. So you trained for two or three constraint, correct?
Mhm.
Of course, it doesn't matter which destination and all, but you trained for this destination, this complexity of constraint. Well, then your model is working for that. But your question is, if there are more constraints, what happens, right? Whether
Mhm.
this model will behave. That's a good question, right? I mean, I think the answer is uh, that is a power of reasoning, right? It's called reasoning power. Smaller LLMs have smaller reasoning, and bigger LLMs will have more complex reasoning power. That means they are trained with more complex chain of thoughts, more thoughts, right? So the answer to your question, yes. If you need a very powerful complex reasoning, you need to have some examples of that. It have 10 constraints or 100 constraints, right? 10 different steps. Then you are training that bigger LLM, right? With the more brain power. So that's how I see it.
Yeah, no, makes sense. Thank you.
Okay, so I was going through one by one here, and then let's say this slide we took it or not. Why is it hard for LL, right? We did see that. Okay. Okay, this is okay. I mean, this is given, I think we talked over that, but it's a good to see it in the print. Anyway, so we went for the equal credit, right? And there are other techniques you can aware of that. Other techniques called temporal discounting, right? Later steps get more credit. That's a temporary. You give the one to the last step which became successful, and then less for the earlier step. And then and there are more complex learned value function, which use external functions to decide. And so these are the different techniques, for oral, but we choose to go with the equal weight for our scenario. All right. Why rewarding the last step is not correct, right? And the answer is you may know that, sometimes the last step, is not the one to make a decision, right? To see whether the whole team or the whole steps did it correctly. So you cannot trust the last steps in the process. So it's better not to judge on last step for any successful steps. That's what this is saying. All right. Okay. All right. This is interesting thing. Let's read through that. If all steps get the same reward, how does the model know which steps were actually good? Okay. This is of course, the deeper or the final knowledge, right, in this oral. So you are telling me, okay, let's give all the reward to same reward to all the steps. But in the successful scenario, in this case, step A, B, C, D, all get the reward 1. But in another scenario, another trajectory, you have a step A, which is actually considered as a good step, right, in the previous trajectory. But it somehow chooses the X and Y and Z, the next steps, due to the stochastic nature of the probability nature. But it gets a final 0, right? But in this case, we are assigning a 0 reward. But in the previous step, we assigned 1 reward. I mean, it looks like ambiguity, looks like it's confusing, because in one trajectory, we are avoiding step A, yeah, you're doing great. In another trajectory, we are saying step A, you're doing bad. So does it not confuse the LLM, when it's fine tuning? That's a question, it's being asked, right? The model sees step A appears in both success and failure, maybe, right? And the step B appears only in success. Step X in the X is appearing in failure. So this is, this, okay. And, you can ignore this question. And then, yeah, right. Okay. A little bit advanced here. And so what, okay, you can ignore this. So what we are trying to say, when you are running this trajectory 100 times, the model comes to know which combination of steps is bad or which combination of steps is good. So not individual, right? That's a key insight. So it learns through and it adjusts its weight by knowing which combination I need to prefer. So that's the idea behind this theory, right? It's okay to give reward, you give reward equally for the steps. It doesn't matter in the next trajectory the same step appeared and it failed. It's okay, you can still give failure, but model knows that the combination of A, B, C, D gets a higher privilege or preference. When in the next time when you ask the model to give the steps. So that's a key insight of the paper. Any questions? To me, it took a while to understand this, but that's a key thing.
Yeah, just to kind of go over what you're saying, I just keeping up here. So it is okay, so earlier you said like, we have the claim of the paper where each step is equal reward if it's correct.
Right.
But what's being suggested here is to not do that anymore, and you can
No.
tricks to do that. Maybe I'm missing something.
No. That's why these questions are a little bit confusing. Ignore that. It is give the equal credit, and it's saying you give the equal reward, but if you're questioning, I'm giving 0 reward in the second trajectory, right? It says don't worry. See, if you're in the second trajectory, the A gets a reward 0, but in the trajectory 1, A gets a reward 1, right? Then the question naturally occurs, am I not confusing the LLM? In one trajectory, I'm saying step A is great. In another trajectory training, I'm saying step A is bad. Is it not confusing the LLM? The answer is doesn't confuse. Doesn't get confused. It looks at the combination of steps, right, in its model behavior. That's what it is trying to say, convey that. It learns through the comparison across multiple trajectories. So that's a deeper insight into the model, how it learns. See, it is,
Yeah.
yeah.
Yeah, so my guess here, and let me know if my intuition is correct, is that like even though we see the weights equal to each other in each step, really what it's doing on a higher level, like when you have your higher level like control neural network um it's coming up with probability distributions within that in that neural network.
Mhm.
It's not just one. It's starting to learn what the estimated equation is for this reinforcement learning
Yeah,
convergence. Yeah.
yeah, correct. That's true. So that's the next thing is, core insight is oral does not learn from single examples. It learns by comparing different attempts at the same task. I mean, that's what we have been telling, right? And we know that we talked about rollout. Rollout is a single in the flow of task to complete a question. That is called rollout. In my example, we run hundreds of rollouts. Okay, and then we I did show that this is how the probability distribution you can imagine in the LLM has that, right? And we are trying to change the distribution, right? If right now this distribution looks good, but let's say that for some reason your current LLM has Paris travel is in the top, right? 30%, 35%. I mean, that's not a good return, good response, the next token response. So we need to retrain the LLM to make this one appear in the top. So that's the purpose of fine tuning. Okay, and yeah, we understood rollout one in our example was great, and rollout two was failure because it didn't book the ticket under 800. Rollout three was successful, though it took a different route to book the same ticket, and then rollout four was also failure. Okay, and so what can we learn from this comparison, right? The outcome is a success, and then observation is specific. That means it's going a little bit detail. The query coming from LLM is very specific. That's why it became successful. LLM is going to, we are just imagining LLM is going to learn that. LLM is observing that why those steps are successful. In other scenarios, the answer was very vague. It's not very specific. So that the subsequent call fails. I mean, this is how humans can judge it, but we just need to extrapolate that LLM is also judging and understanding. Because of the failure steps are vague, it's not going to, once it's trained, it's not going to suggest you a vague step. It is going to give you a specific step. So that then we are saying the pattern emerges, right? Over the training, hundreds of trajectories, we are now able to say your fine-tuned LLM has a new pattern, right? That means it trained itself to give a specific queries, specific answers, and avoids hallucinated queries. So this is what we are trying to achieve by training the LLM. Someone asked a while back, why do we need to train the LLM? Is to create a new pattern, right? That gives the answers very crisp, specific, and doesn't need a lot of prompting. And then also it eliminates hallucination. That reduces the prompting. All these things starts happening. That kind of pattern emerges when you start training the model. All right. I think I'm just skipping those things. That's a concept. Now let's go to the sample code. What I'm not covering today is it's not the end. There is something called policy gradient. Okay. This is I think we are going next level. We talked about oral, we are talking about that, credit assignment. And then the next, what's happening inside the neural network when you fine tune. I mean, that's a big topic by itself. Uh, I think I will avoid that today. We can talk about that in the ML Foundation sort of meetup we may have. We used to have that. We can bring in that the foundational aspect of gradients. Usually, every now and then we provide that in the meetup. We can go through that. But okay, this is visually it's convincing you that before the training, when you ask the LLM, generate search query for New York to Paris, this is a distribution inside the LLM. Visualize that in the LLM. The way you can visualize LLM today without training, 20% of the time it gives this answer. 20% of the time, because it gives the flight to Paris answer. 15% of the time it gives this. This is very bad. This is not good for AI agents because I don't want these bad answers to appear 20% of the time, right? How do I change that? So now, after retraining many times, you are changing this behavior, right? At least now, the one that is appeared to be flight to Paris now reduced to 10%. Okay, I mean, this is kind of imagination. This sort of, you cannot peek the LLM and find this out. It's not possible. But this is the way you imagine inside the LLM. This is the probability distribution. Okay, so this is the essence. Let's pause here and see everyone gets the idea. What happens after the fine tuning? Any questions on this?
So this is for each step of like the agent. And this is the process of how we fine tune it. Is that right?
Yeah, what happens after the fine tuning, right? I mean, and then of course the techniques we talked about. Yeah.
Go ahead.
Yeah, so that's I hope everybody got that, right? That's all the point here. So now anyway, so I'm not going into the probability distribution, right? I mean, there are a lot of things like gradient steps, compute the loss, and then you apply that. So that's beyond the scope of this meetup. So let's go back to the research paper now. So now the foundation is clarified. These are all the, you can say, theoretical foundation behind the oral, right? And then the coding wise, let's touch upon the code and then we'll go back to the architecture and then we will go back to the paper. The coding is pretty straightforward, right? I mean, let's say that I hope some of you are writing the AI agents, either a native or LangGraph or CrewAI, whatever that is, right? You have some agents. And then what you do is, in the code today, if you're let me see, now that we have example of LangChain. So some of you are familiar with the LangChain. So this is basically telling how you wrap up the Lightning framework with the agent. So before this Lightning, you had this, this is a code, this is the agent code you might have developed. You create an agent called agent executor. That's a LangChain LangGraph, and then you invoke a task. That's today's way of doing things. In this, basically agents. Here with the Lightning framework, what you're doing is you are basically wrapping it up, while runtime start the trace. Basically, you're invoking the trace using the Lightning client, and then you are basically calling the same agent. So what the paper is claiming, very minimal changes are needed for anyone who have been developing the AI agents in the left hand side to leverage or benefit from the AI agent Lightning framework by making a small changes. These are the small changes, and then it's able to capture the traces and then able to train the LLM. So that's a claim. I mean, that's what the paper is saying, which is true. I tried it; it is working perfectly, working fine. So this is how you enable, if you're already an agent developer, making this AI Lightning integration is very, very easy process. That's a code perspective. Any questions on this?
Go to the first page with the code.
Yeah, correct.
Yeah, I was just kind of looking at that. Cool, thank you.
Yeah, the same code is in the GitHub, right? You can always take a look, but I just put it here for our reference.
Oh, gotcha.
Yeah.
So is it GRPO next?
Well, what do we do now? So I think GRP is a little advanced concept. I'm going to skip it now, and I can go before. Okay, I'll touch upon that. But this is to overall to summarize what we have learned in the last two sessions. We took an example of this book a flight to Paris under $800, and then for that task, we know that we need to somehow enable the rollouts the way we do it in the agent Lightning, some configuration file. and then say start the training. So then the agent lightning is going to run 4 times or 100 times, doesn't matter. And then it's going to capture the trajectory. For each run, you have trajectories, right? Step 1, step 2, step 3, step 4, step 5. That's called trajectory. So every run has every rollout has a n number of trajectories. And then if you look at the code, we say that in the code, yeah, then the reward is applied automatically, because the framework knows, for successful book ticketing experience, it will give 1 to all the stars in the trajectory, right? And then 0 for failed trajectory, right? And then the framework is taking care of everything else, credit assignment, GRPO calculation, and then policy gradient. So of course, these are all we need to know as what's going inside, but the framework is taking care of all of those internal details, and then finally update the model with the gradient update. So this is the logical steps happening within the agent lightning framework. Okay, so what this is probably missing is the evolve framework. In a real life, you will have evolve framework which actually test it, but that's outside the scope. So this is a flow, right? And then let's see what's next. Any questions before I talk about another concept, and then I will end there. But any questions on this training loop? I think training loop is,
Can you go back to the first part? I blinked.
sorry,
The first like above the trajectories and the diagram.
on the training loop.
Yeah.
Okay.
Yeah, we had your tasks and then okay, yeah, thank you. That's what I was trying to get.
Okay. So next is a single agent versus model, right? I mean, okay, this introduction, we'll have a section on model at some point, maybe in the new year. But what we are talking now is a agent oral, oral for a single agent, right? We are talking about a single agent, which is the flight booking agent, which goes through the multiple trajectories, right, for a given task. But maybe that is not the world we are living in. We are now having multiple agents, a lot of multiple agents, working together, and then solving a super problem. So what does an oral mean in the multiple agent scenario, right? I mean, that's a big question. So this topic of MAL, it's called MAL, multi-agent reinforcement learning. Within the agent training itself, we saw this credit assignment, right, and advantages function, all the things we are understanding. But how do the agents learn together, right? When multi agents need to work together, collaborate together, sometimes even fight together, you can say disagree, and then still need to coordinate. That's called agency, right? So in a mall type of a world, how do we train the agents? That's a big topic. And then the agent lightning doesn't go into that. Agent lightning goes only into the one agent training. It doesn't have the framework to train multiple agents with oral. So there are other frameworks, emerging frameworks, and then there are emerging concept in this. We can cover that, but that's not the scope of that today's meetup. So what else? Next topic in that. With that, we can go back to the research paper, and then yeah, I'm going to stop here now. Let's go to the research paper. Okay. So yeah, so our goal was to let you guys to know more, understand about the research paper, right? We went into a training or teaching type of a route, but the idea was this research paper sort of discussions meetup. Now, a lot of claims made in this paper, right? When you apply the critics, let me show you the important, the concept you understand now. So what is the key thing? Okay. So when you apply the knowledge that we learned through the examples of the flight and all, you visually saw the trajectories and then roll out and then examples. Now you would able to understand. So this is a key piece. These are the three sessions, state and call. Oh, sorry. One second. I kind of. Now you just need to apply your mathematical foundation and then say to enable learning from a collected data during agent execution, we introduce a reward signals to measure task completion quality. Each agent execution is augmented with scalar rewards. For example, we said 0 to 1, where each reward Ri belongs to the reward corresponds to the quality of the ith invocation. In execution with its reward signal is represented as execution of x, part of the k iterations. And then what the call here means, it's assignment of the reward for each of the trajectory steps. That is what this call means here. Reward signals can be provided at either intermediate steps or at the conclusion of agent's execution. What that means, in the example that I showed you, what that means is, the agent lightning framework will collect all the traces, and then for each trace, it notes down the success or failure during its execution, and then at the end, it's going to reward. Right? That's what it means. It finishes the whole operations, and then finally go on to reward the individual steps the credit assignment that we talked. Well, okay, so that's what it's saying there. All right, we can go through that, and then this is an example of how it internally collects it. This is like a technique in which agent lightning. They are basically saying they have a unified data interface. What that means, you saw the code, right? Before the lightning, how was the agent code, and then after the lightning introduced, you saw the small wrappers of the agent code. So what they are saying is that's the behind that it is a unified approach. So how the traces are happening, right? How the traces are added with the reward, how it communicates to the Lightning server. This is all unified. That means there is no change needed. Okay, everything is abstracted. It works for multiple different agent frameworks, and that's a terminology they are calling it as a unified interface, unified data interface. Okay, you can read the user submits a specific task. We did that. Book a ticket to flight. That's what we did. And then agent invokes the LLM to generate such query combined with the user input. The search tool retrieves the relevant passages using this query. Agent calls the LLM again to produce a final answer. I think they are talking about steps of a particular agent goes through in its life cycle. And then they are talking about specific example that they are saying in the reward function. Okay, and then what is Markov decision? I think this is more of a foundation aspect. Markov decision means LLM doesn't have a state. Okay, and every decision it makes is completely not depending upon the previous state. So that's called Markov property. And then why are they saying that is, because of that property, LLMs, the next token prediction or next decision prediction is completely taken care by the current state, not the previous states. So with that theory, they are saying that tracing generated is not influenced, it's not confused by a previous state. Hence, it is essentially a good way to train the RL model. So that's why they are connecting the dots to say that Markov property is a crucial point in training the LLM through the RL one at a time. So that's a theoretical aspect of proving that this RL makes sense. I think the rest of them I'm going to let you read and with the foundation. All right. So what I did not cover is the GRPO. I think it needs a little bit more introduction to various policies like PPO, DPO, and then finally the GRPO. So maybe we should cover it in separate session on that, considering the timing.
Okay. Homework is PPO, got it. With GRPO, I did notice it's not in the paper, so I'm just wondering, is this how you like the way that you would want to tie it in?
The paper is there. It
Oh,
is
okay, I guess my search didn't work. I see. Okay. I look forward to that.
all right. Let me pause here. Any questions? And is it more difficult? I know I want to get some feedback. What else do you want to see this in this session? So on the paper, let's talk about the paper. The paper, I thought about whether paper, how good is the paper, right? The paper mainly tested in a on a specific oral technique. They are claiming that this oral with GRPO they are claiming this is a successful the credit assignment for this scenario making sense to them. But if you apply the critical analytics, a lot of people are claiming that how do we prove that credit assignment equal reward is better or worse? It's just a proposal, and then there is a practical proof, but it's not a conclusive proof. So we cannot assume that equal credit is always better. And then the paper leaves it open to all of us to explore other types of credit assignments, asking us to think about use cases, and then based on that design that credit assignment. So you have to take it with a pinch of salt, right? The equal credit assignment is a proposal by the paper author, and apparently works for their use cases. So we need to apply our own judgment on whether it makes sense to your use cases.
Sounds like you're saying is you're a bit maybe almost skeptic that the claim is true, and I think that's also very interesting.
Yeah, I mean, they themselves agree at the end, right? I mean, if you look at the paper carefully, they ask us to explore further. So, I mean, that's how the research paper are, right? Sometimes they leave it open to you to research. This is a research paper, right? This is not
Yeah.
any product or library selling.
Well,
Yeah.
I don't know if I'd agree with that because it's kind of like hashtag look at our code, hashtag implement it
Yeah.
in our cloud, right?
Okay, I'll leave it to you then.
Yeah, but it's a really interesting claim, and I'd be curious to hear if you think that it would work for most use cases off of your intuition, with a few where it wouldn't work, or maybe vice versa.
Yeah, I want what people think. Let's say what other people think about that. Yeah, any thoughts around that? Where this equal credit may not work. So, I mean, in some situations, right, the important first step is important, diagnosing something, right? For example, you're diagnosing a cancer, something like that. So I'm just making up, right? So sometimes the earlier needs to be done, given more credit. So there are examples you can think like that than the later ones. So I did note down somewhere, but I'm thinking where I note down that example. Let me see whether I have that. But anybody else have other thoughts on that? In terms of should we equal credit makes sense or equal credit doesn't make sense? Any interesting example would be great. All right, I'm not hearing anything. So any other questions or any thoughts?
I was just I was just curious because my question earlier, I don't know if you mentioned your intuition.
Oh, my intuition correct, for the things like ticket booking, AA agents, I see that it is perfectly fine. So in the examples I have seen in the enterprise situations, setups, where there is a workflow to finish some automation, I don't, equal credit is easier to implement. So what I don't have is a not experienced is the situations like life threatening, right? Life situations and stuff like that, where I need to be careful about giving the equal credit. That's my call right now.
Interesting. Yeah, so it sounds like for more like when you think about like a set of problems for automation stuff like booking a flight or just more kind of quote unquote mundane tasks, this definitely would be a thing to use. But for more like critical, there should be more consideration when just assigning a blanket weight that's the same across the board. So yeah, that makes sense. Thanks.
So for example, I did found one of the idea here, I mean in the paper. Okay. So why not earlier steps, right? Problem, we don't always know which step matters. For example, search task, generate a query, read results, summarize. For example, you have a search task, right? The search task, the query in the search is more important. Whether the summarizing is less important, right? Even if it's summarized a little bit differently, who cares? So here maybe we should give the more weightage to the first one. In the case of negotiation, this seems like final. These are all example. I not experienced myself, right? The final deal is more important. It seems rather than the previous steps. Code debugging. If your task is about something troubleshooting, right? And then the what is critical. Critical is about hypothesizing the fix, right? The more critical than other steps, because applying the fix and testing the fix, it makes sense only if you are able to really figure out what the fix is. So in this case, this is important. So I'm just going to leave it open. I don't have the answer. So you decide in terms of your use cases, right? I mean, it doesn't hurt. Putting the equal important may not hurt, but if you think that particular task needs to be awarded more, you can do that. So that's what the paper is saying. Again, the paper is giving that you to decide it rather than it is mandating that. What they're saying.
Yeah,
Mhm.
well, I think I'm gonna say what you're saying is that they're not debating that don't put extra weight on certain things,
Yeah.
but they are saying if you do put extra weight, quote unquote, it'll work. But
True.
obviously,
Yeah.
I'm a skeptic of that.
So the way I'm getting it is right. I mean, it's the paper is probably claiming that yes, it's not going to make a big difference because you're going to learn this as a collectively across multiple trajectories, right? And then don't split your hair and trying to figure it out. Hence, we are suggesting this as equal
Yeah,
weight.
fair enough.
Yeah.
And maybe if you wanted to, you could pick apart the neural network and layers to see what actual weights it is giving attention to as well. I mean, if you
Correct.
really want to, yeah.
Wonderful. I think it's a fascinating area. We are all learning, and I hope I have given you some insights. And wish you guys a happy new year. And then we'll come back and then we'll continue this. Any other question before our final? I mean, before we close out. Thank you, guys. Thank you, everyone. Bye.
Thank you. Bye.
Thank you.